Hey folks, this is the video for, I guess, day 2 of online learning. This is Monday the 23rd. We're going to do another lecture on Fourier series. And in the past, we were doing Fourier series where we're analyzing periodic functions that had a period of 2 pi. So every 2 pi, at least the function repeated, although sometimes it could be even faster than that. So then what happens if I have a function that's repeating every 1 unit, not 2 pi? But if I have it repeating every 10 units, not 2 pi, what do I do? Well, that's what today's lecture is about, Fourier series where I have other periods of length to look at. And so in some sense, there's some bookkeeping that we have to do that's easy. And then if you start thinking about it, you would think about how does that change the Fourier coefficients. There are some some surprising results that when you look at it in hindsight, like, oh, okay, maybe I should have seen that coming. But we're going to work our way through it and see what happens. Okay, so we're going to look now at periods of 2L. Okay, that's the way that it's referred to because it'll be easy just to talk about L and not L over 2 later on. Okay, so the formulas will work out nicer if we make it periods of 2L. And so now, earlier we looked at periods where L was equal to pi because they were length 2 pi. So now we're going to use sines and cosines instead of sine of nx and cosine of nx where they have periods 2 pi. If you think about how to adjust the period length of sines and cosines, they're going to be now of cosine. My handwriting got a little bit sloppy. Well, it got small here. Cosine of n times pi over lx and sine of n times pi over lx. And those each have periods of length 2L. So if f of x is period 2L, we're going to also write f of x as a summation of sines and cosines as a naught plus the summation of all this stuff, where a naught is effectively the same as it was before. It's the average value of the function on that period, on that interval from negative L to L, 1 over 2L instead of 1 over 2 pi. And instead of negative pi to pi, it's negative L to L of f of x. And then a sub n is 1 over L, negative L to L of f of x cosine of that same thing, n times pi over L x and pi over L x for sine as well. All right. So the formulas actually look very much the same. Again, when I'm thinking in terms of my old periods were 2 pi, now they are 2L. I kind of replace all the places where you see pi with an L. And then inside the sines and cosines, we got to make a further adjustment to make sure they have the right length of period. So now let's go ahead and let's look at the example of a step function. This is the first example we did in class, where now instead of having the step function go from negative pi to 0 at negative 1, and then from 0 to pi at positive 1, now we're stretching that out to go from negative 3 to 0 and 0 to 3, overall length of 6. Okay, so here's my graph of it. Here's the formal declaration of it. And the one thing that I forgot to write in here is that as it's written right now, as it's written right now, this function only exists between negative 3 and positive 3. I forgot to add the language that f of x plus 6 equals f of x, like it repeats over time. And so right now it's sort of defined for a very small interval. Let's find the Fourier coefficients. I'm going to skip some stuff. A sub 0 is going to be 0. We predict the average value of the function is going to be 0 because I can stare at it like, yeah, it's negative 1/2 the time, positive 1/2 the time, average is 0. All right, lets you integrate that and see. Now this function looks odd, with a formal definition of what odd means, right? So since it looks like it's an odd function, the even coefficients for the Fourier series, all the cosine stuff should be 0. And now we're going to find out, does it actually work out that way? So again, L is 3, so I'm going to integrate 1 over 3 from negative 3 to 3 of f of x cosine of n times pi over 3x. Now f of x is piecewise defined, so we got to split it up to the negative 1 part and the positive 1 part. That's negative 3 to 0 and 0 to 3. Let's wrote it out now, and now we integrate. And now antiderivative of cosine is sine. And then you got to think about the fact that inside here, I have a coefficient of x, which is n times pi over 3. So I'm going to divide by that coefficient. So I have a 3 over pi n. And I also have this 1/3 out front. And this -1 makes this a -1 out here. So you can follow the calculus through here. Nothing hard, just an antiderivative. It's relatively straightforward. And now I evaluate that integral. Plugging in zeros and -3. Sine of 0 is 0. Sine of a multiple of pi is 0 for all n. Also 0 for all n. Also 0. So I get 0, which is what I expected. Close parentheses. Forgot to do that. All right, what about b sub n? Same basic structure. Again, I have to split it up because it's a trig function, or because it's piecewise defined function. And again, I get 1/3, 3 over pi n. And you work your way through it, just plugging things in appropriately. I get 1 over pi n minus 1 over pi n, cosine of pi, n pi, so forth. And it will take a little bit of diversion. Well, right here, it's 2 over pi n minus 2 over pi n cosine of n pi. And a slight diversion, it says, okay, I know n's an integer. And so cosine of n pi is 1 when it's an even integer. And cosine of n pi is -1 when it's an odd integer. So if you think about reformulating that, we can say cosine of nx is the same thing as -1 to the n when n is an integer. They coincide. So I can take that and replace this part here with this. And I can also write it a different way where I say, okay, when n is an integer, n is an even integer, this becomes 0. And when n is an odd integer, this inside becomes 2. And that makes this whole thing 4 over pi n. And then the amazing thing is that this is the same thing as the square wave that we did between -pi and pi. And so you got to think about, why is that true? Why is it the same thing? And then if you start thinking about functions and function behavior, remember that when you multiply, if you have a function f of x, if you multiply that x by some sort of constant like f of kx, that stretches it or dilates or shrinks, whatever, that function. It's a stretching factor. So I want to take my old unit square wave and I want to stretch it. And then I also want to say I'm going to approximate this with a bunch of sines and cosines, but actually not any old sines and cosines. I'm going to take the old sines and cosines and I'm going to also stretch them. So what are the coefficients for the new stretched sines and cosines? Oh, well, it seems like I could just take the old coefficients for the old sines and cosines, we'll leave the coefficients alone and just stretch those sines and cosines, and now I will match the new stretched function. All right, so I guess, you know, the Zoom TV thing going on here, you might have to replay that part again. But in my mind, I have a function is equal to a sum of sines and cosines with coefficients up front. I've stretched this one, and if I stretch the sines and cosines, then the coefficients should just be the same, because this, the effect of stretching this is accounted for by stretching this, and that's all I needed to account for. So it's pretty cool that it's actually the same thing. So there you go. Not much to this. Now we're led right into a homework assignment. And it's only one problem, which is I'm going to tell you the function f of x is just x between -2 and 2, with f of x plus 4 with f of x. Tell me what the period is, and then do the work to find all the coefficients of the Fourier coefficients, a0, an, bn. Find them all right? And then you should be able to predict what each one is. Well, you should be able to predict 2 of 3 of these coefficients, but then show me what it is. You can use a little bit of technology to help you with the integration step. You will need integration by parts. We've seen this stuff before, not too hard. All right, and then upload it online. And again, you can find me, email me, or meet me in a Zoom classroom if you need help. All right, that's it from here. So again, I hope you're doing well, and contact me if you have questions.